In this lesson, we are going to review electron configuration of period 4 elements, how to identify the valence electron configuration, and then we are going to shift to practicing using PES to identify elements and to identify electron configuration. And then finally, we are also going to answer a review question in regard to effective nuclear charge. So let's take a look at these four period 4 elements. We'll start with scandium. And let's see, I want to change my color. All right, so the electron configuration for scandium, or scandalous as I like to call it, will be 1s2, 2s2, 2p6, 3s2, 3p6. All right, and out here we're at 18 electrons, right? Then we're going to have the 4s2, and then we're going to have 3d1. The valence includes the 4s and the 3d, so I'm going to box it in here. And for some reason, students like to separate these, and you should not do that. This represents the valence of a period 4 element. Remember that period 4 elements, they preferentially I don't know if that's spelled right. There could be just one L on this, but I don't care. So this is going to be preferentially ionize the 4s electrons before 3d. And you'll recall from the PES videos that we did before this that if you look at the electron configuration the way it's written here for scandium, that this was written to follow the quantum mechanical model, but based on this information right here and the PES data, you could argue that the 4s should follow the 3d because the 4s electrons are at a higher potential energy than the 3d electrons, and we know this because the 4s electrons preferentially ionize. Now, I have chosen to put both chromium and copper into the 4 elements that we're working with here because both of these are exceptions to the electron configuration or the Aufbau principle. They're exceptions to the Aufbau principle. I'm going to say that a third time. They are exceptions to the Aufbau principle, so I'll put a star by both of these. So for chromium, the configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, so we're at 18 at this point. And then what makes these distinct is that only one electron goes into the 4s shell. All right, and then we're going to have 3d, change my color again, so we're going to have 3d5 here. All right, one electron in the 4s shell. The valence, so I don't forget myself here, is 4s1, 3d5. I'll circle the whole thing. This is the valence. It includes the electrons in the 4s and the 3d. Remember in period 4 that that there is a similarity in energy between the 4s and the 3d. And as we proceed across period 4, by the time we get to zinc, there is a shift in energy level 3 into lower energy, where the 4s electrons are definitely higher in energy, which explains why zinc ionizes to only one oxidation state, which is Zn plus 2. All right, let's take a look at iron. It's going to be 1s2, 2s2, 2p6, 3s2, 3p6. Again, we're at 18 electrons at that point, and then we're going to have 4s2. That's 20 electrons and we are left with 6, so that we're going to have 3d6. So we have 18 at the 3p subshell, we have 20 at the 4s, and then we have 6 electrons to go into the 3d. Remember that iron readily forms iron 2 and iron 3, and also on rare occasions iron 1, as well as there are other oxidation states. And so one of the observations that you need to think about is that the elements that are in the middle of period 4 have a lot of oxidation states. And what that implies is that the valence, which is the 4s and the 3d, have the most similarity in energies in the middle of that period, which is why you see the middle elements having such a wide variety of oxidation states. Now finally, we'll look at copper. This is going to be 1s2, 2s2, 2p6, 3s2, 3p6. Again, we're at 18 at this point. And then this is one of the exceptions. So I'm going to change color. One of the 2 exceptions. So this is going to be 4s1. And then to finish this guy out, we're going to have 3d10. And again, the valence is the 4s and the 3d here. The common oxidation states of copper are going to be Cu plus 1 and Cu plus 2. Remember that period 4 elements preferentially ionize the 4s electrons before the 3d electrons. So anytime you are asked to write the electron configuration for an ion out of period 4, you must preferentially ionize the 4s electrons before taking anything out of the 3d. Once you have rectified how many electrons have come out and whether or not the 4s is still full, then it is your responsibility to write the new electron configuration. All right, now let's move on to the questions in this lesson. Question number 1. Identify the element based on the following PES diagram. Note the number of electrons are on the left side. Note the proportionality of the peaks. Write the electron configuration. Or excuse me, in this one you're identifying the element. All right, I'll put a question mark and then element. Here we go. Question number 2. Identify the charge on the cation based on PES. You're given 2 PESs. You're given the PES of the neutral element shown here. And then you're given the PES after the ionization takes place. Good luck. Question number 3. Identify the electron configuration and the element. So here you're doing 2 things. You're identifying the electron configuration correctly and the element from the PES. Question number 4. Given the PES, identify the valence electron configuration. You are being asked for the valence electron configuration. The valence electron configuration based on the PES. Question number 5. Identify the valence electron configuration based on PES. Identify the valence electron configuration based on the PES. Question number 6. Calculate the Zeph of the 3s2 electrons in zinc. I'll read it one more time. Calculate the Zeph of the 3s2 electrons in zinc. All right, good luck.